Given the 2 by 2 matrix A with elements A, B, C, and D, the matrix A has an inverse only if A inverse is equal to 1 divided by the determinant of matrix A times the matrix D, negative B, negative C, and A. So keep in mind, when looking for the determinant of matrix A, we will do so by multiplying diagonally the elements of our matrix, beginning with A times D, and subtracting that from the product of B times C. This formula will only hold true for our matrix as long as the determinant of matrix A does not equal 0, in which case our entire fraction right here would be undefined. Let's look at our first example. I'm going to first label the elements of my matrix, A, B, C, and D, and I'm asked to find the inverse matrix. I'm going to indicate the inverse by using a -1 as my exponent to find P inverse. According to my formula, the first thing I want to do to find my inverse is 1 divided by the determinant of my original matrix. So that's going to look like 3 times 2, which is 6, subtracted from 1 times 5, which is 5. I'm going to multiply this fraction, 1 over 6 minus 5, by a new 2 by 2 matrix. If you look at our formula, first we have the element D and the element A from the original matrix. If you look at the original matrix compared to our formula for finding the inverse, all that we're going to do is reverse the values that are in the D and the A position. So, on my diagonal, I'm just going to reverse the order of the 2 and the 3. Next, if you look at my formula, I'm going to take the elements B and C from the original matrix, and all I'm doing to find the inverse is changing the signs. So this would make my B value a -1 and my C value a -5. Now I'm ready to simplify. 1 divided by 6 minus 5 just gives me 1. 1 over 1, but I can just write that as a 1. And I'm going to multiply my 2 by 2 matrix by +1. This means each element in the matrix will get multiplied by +1, making my answer for P inverse the 2 by 2 matrix with the elements 2, -5, and -1 and 3. For my next example, I have the 2 by 2 matrix R, and we're looking to find the inverse matrix, R inverse. The first thing I want to do, according to my formula, is find the determinant of the matrix that I have. -4 times 6 is -24, subtracted from -3 times 8, which is also -24. I will be multiplying this fraction by the 2 by 2 matrix, in which I flip the position of the -4 and the 6, and I change the signs of -3 and +8. Now I'm ready to simplify. In my fraction, 1 divided by -24 minus -24 will give me 0 times my matrix, And now if I go to solve this, we have an issue. 1 divided by 0 is undefined. We're not allowed to divide by 0. And because the determinant of our matrix turned into a value of 0 right here, that means my answer here for our inverse is that it does not exist. Next, we'll discuss the identity matrix. The identity matrix is as follows. The 2 by 2 matrix that has 1s on its diagonal, going from the top left to the bottom right, and 0s on the second diagonal, going from the top right to the bottom left. You can determine if two matrices are inverses of one another if their product is equal to the identity matrix. Multiplying by the identity matrix is the equivalent of multiplying a constant by 1. You would get the same value back again. Let's look at an example. We're going to determine if P and Q are inverse matrices of one another. And the way that we'll do that is by finding the product of P times Q through matrix multiplication. So as a quick review, we're going to take the first row of P times the first column of Q, and we'll begin by multiplying 2 times negative 1 and 3 times positive 1 and adding those values together. So the first element in my matrix is a 1. Next, we are going to multiply 2 times 3, which is 6, and 3 times negative 2, which is a negative 6. So the second element in my matrix is 0. Now that we have used the first row of the P matrix, it's time to use the second row of the P matrix with the columns of my Q matrix. So 1 times negative 1 is negative 1, and 1 times 1 is 1. Their sum gives us the third element of 0. And lastly, we'll take our row, our second row, one last time to multiply it with the column of Q. 1 times 3 is 3, and 1 times negative 2 is a negative 2. 3 minus 2 gives me 1. Since P times Q has given me the identity matrix as my answer, I am allowed to say that P and Q are inverses of one another. Let's look at a second example. We're now going to find out if the matrix A and the matrix B are inverses of one another by repeating the same process of matrix multiplication. The first row of matrix A times the first column of matrix B will give me negative 4 plus 5, which is 1. The first row times the second column of matrix B will give me positive 10 minus 10, which is 0. Now that we've used the first row of matrix A, we're ready to use the second row of matrix A times the first column of matrix B. Negative 1 times 2 is negative 2, and 2 times 1 is 2. Their sum gives me 0. And negative 1 times negative 5 is a positive 5, and 2 times negative 2 is a negative 4. Once again, through my matrix multiplication, I have a product which the solution is the identity matrix. So I'm able to say A and B are inverses of one another.